Hello, everybody. We are group number 3, and today we're going to be discussing pumps under pressure. My name is Tyler Burton.
My name is Bryson Strimler.
And I am Lauren Inamorado, and I'll get us started. So our overall system that we decided to choose was a pump, a fluid pump. These are used to move liquids, gases, and slurries, and they are vital to a lot of workplaces and manufacturing centers. They have an inlet connected to a volute, which is the circle picture on the diagram, and an outlet connected to that as well. The picture shows the vertical orientation with a height h. They typically operate by rotary equipment, which would be a rotating impeller within the pump, or a reciprocating equipment, which usually involves some sort of piston. Both of these will achieve a pressure distribution, which is what a pump is used for. You will pick between the two based on the task that the pump is being used for. These also can come in different shapes and sizes. For example, the microscopic pump you could use in a heart pump or a diabetic pump. If you wanted to use a macroscopic pump, you would use that on an industrial site to do with oil or water or something like that. The energies in our system are described in the textbook, and they are assumed to be adiabatic and reversible. Both of those properties automatically imply an isentropic process, which is where the entropy remains constant throughout the entire system, which is the delta S is equal to 0. And it also lets us use delta H is equal to the shaft work, which is W subscript S. This equation allows us to apply a lot of things to the situation and describe the work at the outlet. And because we are assuming, and we also know that energy is always conserved, we can also look just at enthalpy, the change in enthalpy, which we will see is the primary source of energy that will create the pressure gradient, which again is how pumps need to operate. We will also see that the physical orientation of the pump matters. If you are using it in a vertical orientation, the force of gravity is present, which does work on the system. The potential energy term is present in the energy balance. If you are using it in a horizontal fashion, the force of gravity will be absent. So this potential energy term will also be absent. Now I will hand it over to Bryson to discuss energy conservation and those associated equations.
Thank you, Lauren. So how can energy conservation be defined? The conservation of energy was first believed to be a purely mechanical process, which accounted for the kinetic and potential energy in a system. A system is defined as the body or assemblage in which the forms of energy are taking place. As well, the surroundings should be included, which accounts for everything that the system interacts with. However, with advancements in technology, it has become apparent that the heat and internal energy of a system must also be included. The first law of thermodynamics states, although energy assumes many forms, the total quantity of energy is constant, and when energy disappears in one form, it appears concurrently in other forms. It is also important to know whether the system is open or closed. A system is said to be open when matter crosses the system's boundaries, such as steam, or in this case, water, and closed when matter does not cross the system's boundaries. When the system is open, the flow rate of matter must be incorporated into the overall energy balances, which will be looked at next. So as you can see by this first equation, this is the general energy balance for all types of processing equipment and forms of energy. As you can see, the dm over dt term is canceled out, and this is because it is assumed to be a steady state flow process, where the change in mass is 0, where the fluid coming in is equal to the fluid coming out in terms of composition. Moving on to the second line, we can see that the velocity term u and the q term are also canceled out, where the velocity is canceled out because the initial fluid has the same velocity as the fluid exiting the pump, and q is equal to 0 because of it being an adiabatic process, which means that it's isothermal, so no heat generation is taking place. This then leaves us with two different types of equations for shaft work, the first one being on the left and the second being on the right. The one on the left is as Lauren described, where it is a vertical orientation, meaning that elevation must be accounted for, and this is because the work due to gravity must be accounted for. On the right, we can see that the shaft work is just equal to the change in enthalpy times the mass flow rate, and this is because there's no elevation change due to it being a horizontal pump. This leads us into the conversion of energy. So how do we convert energy? And what is it? Energy conversion is concerned with the transformation of one form of energy into another. This is done through the use of processing equipment, which are tools used to harvest a specific form of energy and convert it into another. In this case, a pump is being used to move a fluid from a lower to a higher elevation. A low pressure fluid will be fed into the impeller eye, as seen in the diagram below. As the impeller eye and blading rotate, the pump will transfer its work to the fluid in the form of momentum, which ultimately increases the velocity of the fluid inside of the pump. The pump also has a volute region, as shown below, which is designed to have an increase in cross-sectional area as you get closer to the discharge area. This space is used to convert the fluid's kinetic energy into pressure, which is what allows the fluid to be dispersed at higher elevations. So in this case, the pump is an open system as water is flowing in and out of the pump. This moves us forward to the mass flow rate of our system. So in this case, we're going to be looking at a kitchen sink, as that is probably something that everyone deals with daily. Since a kitchen sink is being used, it was assumed that the fluid moving through the system is water, so no density conversions were necessary. This is because the volumetric flow rate is approximated to be 2.2 gallons per minute, and then once again, it is just water going through, so the density is consistent. In order to convert the volumetric flow rate into a mass flow rate, the gallons were converted into kilograms, and the minutes were converted into seconds, as seen in the math on the slide, leaving us with a mass flow rate of 0.13879 kilograms per second. We will now go into the degrees of freedom, which is going to be discussed by Tyler.
Thank you, Bryson. So when conducting a degrees of freedom analysis on our system, it is imperative to both consider the mass dynamic and thermodynamic aspects. Initially, the degrees of freedom, or the general degrees of freedom, must be accounted for by using the streams, species, temperatures, and pressures. These variables are all taken into consideration as there are two streams with one species and a constant temperature. As the pump increases the pressure of the outflowing fluid, there must be two pressures in the general degrees of freedom. These added together total 7. So with respect to the general constraints, material balances, stream constraints, other constraints, knowns, and temperatures must all be examined. As previously mentioned, there's only one species and therefore only one material balance. This also comes into account when writing stream constraints, as the mass fraction of water in both is 1. Since the system is both isentropic and adiabatic, the total work done is directly related to the change in enthalpy. Thus, there is no change in temperature. This allows for the vast simplification of the equations needed to completely specify a pump. Using a simplified form of the energy balance, equation 1, as our other constraint, it becomes apparent that the total number of constraints is 6. So, subtracting the general degrees of freedom from the constraints leads to a total of 1 degree of freedom. This, however, can be accounted for when given an initial pressure. Next, I'm going to talk about system properties. So, an intensitive property is one that is material specific and does not depend on the amount of the material. In our system, there are 3 main intensive properties that apply: density, specific volume, and pressure. With this being stated, pressure is the only intensive property in a pump that changes, as there is an increase in fluid pressure once it flows out of the pump. The direct opposite of an intensive property is an extensive property, and that does depend on the quantity of the material. So extensive properties that we are concerned with are the mass flow, enthalpy, energy, and volume. Enthalpy is the main property that is changing in our system and is doing so as a function of the amount of energy being added. Since the system is isentropic, the enthalpy change is the direct function of the total work. It is assumed that all the other properties are static. Thank you for listening to our presentation, and we hope that we were able to effectively inform you about a generalized pump and how it may apply to your everyday life. We now open the floor to questions, and thank you for listening.